How's everybody doing tonight? Good. Everyone's good? All right, I do speak quickly. I feel very bad for the translator wherever he or she happens to be. So I'll try to keep at this pace. Okay, I'm glad everyone's doing well. This is a great honor. Thank you to the organizing committee for having me here to speak to you guys today. And special thanks to Professor Gazayas for inviting me. Let's all give him a round of applause. This is awesome. He's been a huge hand. Thank you, thank you. No, I wouldn't be here without you, man. Come on. Okay. So yes, I'm here to talk to you guys about our local universe. And our local universe, as far as galaxies are concerned, is pretty complicated. So what I'm going to try to do is walk you through and understand what galaxies are, how they form, how they organize themselves, and then we'll start looking at the details of our little neighborhood and the weird peculiarities in that. So starting off with galaxies. All right, we're good. Can you guys see that? Is that okay? Okay, good. The lights aren't too bright? Okay, awesome. So there are two categories of galaxies I want to talk to you guys today. There's tons of galaxies out there, but I only want to mention two. And the two types are disk galaxies and elliptical galaxies. Disk galaxies actually are flat, they rotate, and they have wonderful structure inside them. So you can see there are these bulges, as well as spiral arm structure. So disk galaxies are typically forming lots of stars. Everything's very exciting in a disk galaxy. On the other hand, you have elliptical galaxies, and they're kind of like a beehive. They're just stars. They're kind of flying around doing whatever they want to do. There's no organization, and there's no new stars being formed. They're very old. Now, the way astronomers talk about these is we actually plot their colors versus their what we call absolute magnitude. This is just the total brightness, all the light coming out of things. It's not that important, but I want to point out that it turns out that the ellipticals are red, and they're red because there are no new stars forming. So this is a very easy way to determine what galaxy you're looking at. You don't need a perfect picture. You can just plot this diagram, and you get all the ellipticals here, and you get the disk galaxies down here in the blue, and the blue, again, is a result of star formation. Stars that are forming in a galaxy are going to push out a lot of blue light, more than the red light, and hence the galaxy will end up here. There is this thing called the green valley. It's not really that important. It's basically a hybrid between the two. So that's great. We've got our two main characters of our story, right? We've got our elliptical galaxies, we've got our disk galaxies, we're on our way. Now we want to understand how a galaxy forms. So there's two possible theories that go on currently for galaxy formation. One of them is the monolithic collapse theory. Basically says nature takes over. There's a bunch of stuff, there's a lot of stuff, gravity wants it to contract, and so it does so. In the other case, hierarchical clustering, you have little spots of material everywhere, and they smash into each other to make bigger things. Hence, I say nature versus nurture. Nature is you just have material, it does what it does. In this case, it's all about the environment. If you really want to know the truth, I think it's actually a combination of both that we have to apply in physics, but we like to talk in these two regimes. So I'll walk you through those very simply. In the monolithic collapse scenario, you have a bunch of gas and dust. This is how galaxies start off. This is how stars start off. So you end up basically collapsing that, and if there's no rotation, you end up forming an elliptical galaxy. Pretty simple. It just collapses in on itself, it starts making stars as it starts collapsing, and you end up with an elliptical galaxy. In the case of a disk galaxy, all you need to do is the exact same thing, but spin it. And the moment you spin it, it forms a disk, and that disk starts making stars, and it'll continue to make stars. It's not as efficient at making stars, so you end up having basically new generations of stars forming in the disk. So it'll continue to be blue, like we mentioned. Hierarchical clustering is you end up with little blobs of things that will coalesce due to gravity, and then they'll smash in and make bigger things. So you have two little galaxies, and they smash together, make a bigger galaxy, and you end up with the biggest galaxies. So what you can end up doing, though, it's a little hard to think, if you keep smashing galaxies into each other, you might not be able to form an elliptical. It's very relaxed. It's a pretty chilled out galaxy. It doesn't want to do very much. But in this case, the way you get an elliptical galaxy is you have mergers, and they shoot off stars into the universe. And those stars end up sitting somewhere. And they find this nice little resting spot, and they will form this very weird arrangement of stars that end up being just random, which is exactly what you see in elliptical galaxies. So with that being said, we have our galaxies, disks and ellipticals. We also have how they form, Now, this is how they arrange in the universe. This is the cosmic web. It looks like a web, like a spider web. Every single point in this diagram is a galaxy. We're located right here, and we're looking out. So this is distance, and those are different galaxies. The color change from red to blue, from red to green to blue is just to show you the distance change. And you notice there's all this structure. It's not random at all. There's organization. This is actually what I work on. I try to figure out all the patterns that are going on in there. So you can see there's all these beautiful galaxies, and that's what they look like. Now, if you look at the night sky and want to see the galaxy distribution, this is what it looks like. The colors, again, mean distance. So starting from the sort of purple end all the way to the red, all those galaxies are moving further away. And you see this wonderful structure. You see these filaments going down here. You have all sorts of weird structure. You have areas. Now, I should point out, this area right here, that's not real. That's a problem. We live in the Milky Way galaxy, and that galaxy is full of dust, and dust is not friendly to light. So what happens? The light comes in, hits our galaxy, and disperses. We can't see anything past that. So this is an artifact of the fact that we live in the Milky Way. So there are galaxies back there, we just can't see them. But look at this beautiful structure here. You've got these open voids where there are no galaxies, and then huge clusters. Incredible stuff. Cool. So now I'll describe a little bit of how we make sense of that. The first way is actually looking at spherical arrangements. Excellent. Thanks, guys. So spherical arrangements. So you can pretty much assume a sphere, and you have wonderful clusters like this. There's about 150 galaxies in a cluster like this. And they pretty much make a sphere, and I'm going to explain this distance. I say 1 to 5 megaparsecs in diameter. So you have a sphere, the diameter is across it, and basically you can think between our home galaxy, the Milky Way, and our nearest galaxy, which is the Andromeda galaxy. Doesn't matter, I'm just telling you. If you don't believe me, you can look it up. But there's a really big galaxy right next door to us. And the distance between us two is actually about 1.8 megaparsecs. So we'll assume that's 1 megaparsec for the rest of the talk. We'll just say units between us and our neighboring big galaxy. That's all you need to know. So the next type of structure you can end up having is a cylinder. And this is a beautiful representation. These are all galaxies in here, and someone went out and observed with radio, hydrogen, that connects every single galaxy together. So this is a cylinder, and so you expect the extended length to be about 10 to 50 megaparsecs, and the diameter to be 5 to 10. So we're getting a little bigger, right? These structures are a little bit more larger compared to the spheres, and the largest of them all are sheets and walls. I say this with a little asterisk. That was up until 5 years ago, and we'll get to that in a second. But this is a wall. Now, it might look funny. You expect a wall or a sheet to be this extended object, like the top of this box, right? That's going to be a sheet. But no, what you're seeing here is actually top down. So you take your sheet and you flip it, and you look down, and that's actually what you're seeing there. And this thing is huge. It's 100 megaparsecs. That's 100 times the distance between us and our nearest galaxy. So that's pretty impressive. And it's only about 5 to 10 megaparsecs thick. So these are the biggest structures in our universe. Remember, guys, just in case I lost you, all these points, they're galaxies. This is big stuff in the universe, right? So how do we make sense of this? Well, it's great we found it. So we know it's out there in the universe. Now what we need to do is actually understand it mathematically. So any physicists in the room probably know this joke. How do you make an approximation of a cow? You make it a sphere, so on and so forth. We know. So we move forward, and what we do is we actually approximate our theories using dark matter. Now, if you don't know what dark matter shows up in this way. So if you have a galaxy, this is, by the way, our neighboring galaxy, the Andromeda. And if you just look at the light, if you just add up the light along the radius going this way, that will pretty much tell you how much stuff is there, right? If there's a lot of stuff, it'll be very bright. If there's not a lot of stuff, it won't be very bright. Kind of makes sense, right? So what astronomers did was they added up all the light along the radius and then expected that because that means how much stuff is there, you can predict in the red line how the motion of the stars will rotate around the galaxy. So that's what I've plotted here. You have a rotation, that's the speed of rotation around the galaxy, versus the radius, which is just the distance out from the center out this way. And the red line is the predicted curve. And then in the 1970s, they went out and they measured it. And they measured the white curve. Well, that's a pretty big problem now, isn't it? So what they realized was they had to correct for something. And the correction is they had to add more mass to the galaxy. That's what dark matter is. So we have to start looking at things simply, and the nice thing about dark matter is it doesn't deal with light. It only wants to have communication through gravity. So it's a very simple model. We don't have to worry about other fields of physics like electromagnetism. Doesn't matter. All we need to know is Einstein's equations, and we're good. So we went ahead and did that as an astronomy community. The good thing, to show you that the assumption is correct, we can use dark matter, is dark matter makes up 85.5% of the matter that we know of. So the stuff we're made out of, the stuff on the periodic table in chemistry, it's only 14.5%. So it doesn't really matter. It's an additional correction. But we seem to be getting it right. This is a simulation of a universe, and these are galaxies, only done in dark matter. It's starting to look pretty good. So we did it again. And we went ahead, and this is our observed universe. This is our universe. These are real galaxies. This is a computer simulation. The difference between these two patterns is 0.2%, only with dark matter. We're starting to understand how galaxies cluster. This is very good. We're getting even better. So we're starting to add all that crazy other physics in there. The electromagnetism, the stuff that dark matter doesn't deal with, but our matter, baryonic material, the stuff on the periodic table, it deals with. And so here you've got dark matter, here you've got gas temperature, gas velocity, gas density, and lo and behold, they're making really good-looking galaxies. These are all fake. These were all made on a computer, and they look amazing. So we're getting really close to understanding all the physics from building a galaxy to how they congregate and cluster together. So now that we understand the cosmic web, we've seen where simulations have gone, we understand the mathematics that we've gotten together, let's take a trip back home. So in this image, this is real data, guys. I know the resolution is kind of poor, but believe it or not, this is real data. This is our neighborhood. I want to actually refrain from saying that word. I'll use it later. But this is our region of our universe, and we're right here. We're right there. So let's zoom in and see what's going on there. This is our home. This is what I want to call our neighborhood. It's actually called the local sheet. There you go. This is us. This is the Milky Way galaxy. That's the Andromeda galaxy. And I want you to focus on the yellow galaxies. Those are the big, heavy galaxies next door to us. Because gravity pretty much only cares about the big and heavy things in the universe. It turns out that the thinness and the length of this sheet is literally like my cell phone. This is really weird. When I saw this, I didn't believe it. Gravity does not want to have small sheets like this. That's what all the theories say. This shouldn't be, and we live in it. So it was my job to go and figure out why this was. So I took it upon myself to do this. It was kind of fun. So here we have all the galaxies. I should point out there's 12 disks, 2 ellipticals in there. And I'll point those out later. But we'll do a little experiment. There's actually a cool question you can ask. Not only do you look at the arrangement of the galaxies as a sheet, and I should point out, sorry, let me back up a second. There literally are no galaxies above or below. This is not a, we didn't look, it's not that we didn't look there. We've scanned the entire sky. We know every galaxy out to this distance. We know this. And there is nothing above or below making this a perfect sheet. So we asked a question. Not only do we know the organization of galaxies in our nearby neighborhood, but we can look at the orientation of galaxies. So we can define the top of a galaxy by the way it spins. And that gives a direction on the night sky. So you have a galaxy, it's tilted, and it spins, and you know that it's pointing in that direction. That's actually really crucial information to understanding how that galaxy ended up there. So we can look at the rotation. We know it's a plus on this side, minus, it's rotating, it's doing its thing. You get a vector. It points somewhere in the night sky. We can look at all these pieces of information and try to make sense of what the universe has done to our neighborhood. And I should point out that the prediction from theory is that all the galaxies will lie on their side. All the tops will point in the plane, never out. So that's the way we kind of expect things to go. Now this plot looks kind of confusing. Trust me, I'll explain it in 2 seconds. Don't worry too much about it. What you actually have here is all these closed circles. Those are the tops of the galaxies in our sheet. And if you look, it makes a huge circle on the night sky. And if we just step off our sheet into the galaxies just beyond, those tops are all pointing along this. These two are completely different geometries. And you would expect, because we're the smaller sheet, if you will, in a larger region, we should be doing what the bigger thing is doing. So we would expect for our sheet that you'd have this, but you don't. You have a circle, which is very interesting because a circle is not random. It's very well organized. So something has happened to our neighborhood. And what I think has happened is the Milky Way and the Andromeda Galaxy caused this change. They flipped their neighbors. And the reason this is actually possible is because the local group, as we call it, the Milky Way, the Andromeda, actually contain 27% of the mass of the entire sheet. Additionally, they're near the center, so they can bully their neighbors equally, because all gravity cares about is how far you are from them. And lastly, there are two galaxies, which helps a lot. If you have two galaxies, you can flip things a lot easier than if you have one. I should also point out that this is a top-down view of our neighborhood. There's something else going on that's very weird. There's a ring. There's an absolutely perfect circle of galaxies around us, which is extremely rare. You never see this sort of thing. So again, this is something that we're looking into. But totally cool. That is just wild. So what did I do? I decided to go and answer this question. Remember, we think the local group, us, and the Andromeda Galaxy has caused this spin flip, if you will, or flipped over the galaxies in our neighborhood. So I went out and I found copies. I made a mathematical model and I found copies of our neighborhood. And the way I basically define this is I want to keep these four galaxies the same. I forgot to mention, these two galaxies down here, they don't look that special. They're just big and yellow. They're the only two elliptical galaxies in this entire sheet. And they also comprise 27% of the mass of the entire sheet. Furthermore, just for fun, I don't know what it means, but I kept it the same. They're literally 180 degrees away from each other relative to the Milky Way galaxy. Just highly weird, you don't get this kind of alignment. So I figured I'll keep that in my model. So I basically found these four galaxies. I want to preserve a Milky Way and Andromeda galaxy, make sure I have two ellipticals, and then they're surrounded by a sheet of galaxies. So I went hunting. I got a whole catalog of galaxies, which was so much fun. Tons of data. So again, we're here, and all these, in fact, I got another data set that goes even further, which was pretty wild. So lots of cool stuff. The reason I looked at this, I'll explain, was we actually get imaging. So forget about this, it just tells you which colors we look at. You get imaging, which tells you two dimensions, right? So when you take a picture on the night sky, you have an X and you have a Y. On top of that, it actually gives you a rainbow or a spectrum, and the spectrum gives you the Z. So you know the distance to your object. Remember, a sheet is a three-dimensional thing. So we need three-dimensional data to make sure we find sheets. Makes sense, right? Cool. Actually, I'll tell you a cool fun fact. This telescope doesn't work like most telescopes. Most telescopes, you grab, you point at something, you're like, yeah, that sounds cool. No, this telescope just sits there, and it can move up and down and so on and so forth, and it lets the Earth rotate past it. And it has 54 seconds to take an image, get it, process it, put it away. That's everything. So it's a pretty neat telescope. So again, other people did this in the United States. I didn't do this, I just got the data. But once we got the data, I was able to search through 1.18 million galaxies. It was a little difficult, I'm not gonna lie. But we actually found 174 copies of our neighborhood in the nearby universe. So here's an example of one. It's from two different angles. You can see the members are highlighted in larger circles. You have the interacting pair, which is the red. You have the elliptical galaxies, which are the blue, and then the members, which are the dark black. The nice thing is you can see there's actually no galaxies above and below for the most part. So the voids are preserved, hence you have the definition of a sheet. So this is awesome. We found copies of ourselves. That's pretty cool. Now what we need to do is test our hypothesis. We said the local group, Milky Way, Andromeda Galaxy, flipped their neighbors, right? So to do a proper science experiment, we need to find exactly the same setup without us. We think we're the problem, right? So we need to take our galaxy out, we need to take our friend, the Andromeda Galaxy, out and replace it with something. And so that's exactly what I did. We have our local sheet. there's our two galaxies, the Milky Way, the Andromeda, and I ran the same code to find copies, but I made a different constraint. I said, let's find a really small single galaxy there. Because if that's the case, we shouldn't see any spin flip. And so I did that. And the way we go about measuring spin, or measuring the tops of galaxies, is we look at the way galaxies are aligned on the night sky. So this is considered face-on, so you get 90 degrees. This is edge-on, and you get something like 0 degrees. It's a little bit more than 0, because they're thick. And again, the prediction is you're going to see, in the sheet with no local group, with no Milky Way Andromeda galaxy, you're going to see this alignment. You're going to see all the galaxies flipped and their tops pointing into the sheet. So I selected only sheets that we see face-on. So the sheets are upright. You're looking at them this way. And that's the prediction. This is the distribution of those, what we call axis ratios. It's just the shape of a galaxy on the night sky. And the prediction was they're all going to be low numbers. They're all going to be down here. So this is with the Milky Way and the Andromeda. This is the distribution. This is the distribution for the sheets that don't have us. No Milky Way copy, no Andromeda copy. They also don't cluster down here. So something, first off, seems wrong with this theory, which we're investigating. In fact, that's most of my PhD. But what's really neat is the difference between these two distributions is 97.6%. So I think we've done it. We've shown concretely, just with that simple test, that the local group, our galaxy and the Andromeda galaxy, flipped their neighbors, adding yet another chapter to the Milky Way story, understanding our origins in the cosmos. This is very cool. So since we're talking about the Milky Way, I figured I'd continue forward. This is the Milky Way, the way we see it. I hope everyone has taken a trip out of Athens, maybe, and actually seen this at some point in your lives. It's worth it, I'm telling you. It's very philosophical. It's nice. So you get to see this beautiful band of stars. You have all this dust, all these just gas. It's very, very cool. And you can tell it's a disk, right? Like it's not this beehive-type galaxy. It's not elliptical. It's flattened. There's another image. It's a composite image, taken from the Earth, of course, but it's just absolutely stunning. And we have our companions, Large Magellanic Cloud, Small Magellanic Cloud. Very cool. And we're located about halfway from the center to the edge of the galaxy. Next to us is the Andromeda galaxy. Did anyone ever use a Mac before? No? Maybe? Something? Well, this was the default background forever for Mac, so it became very popular in the mid-2000s. And it also has a few companion galaxies there and there. So remember, this is the theme of my story, right? We're talking about these two galaxies. But now let's talk about their evolution. Their evolution actually is very bizarre. They're actually flying at each other. There's no circular component to their orbit. They're literally going to crash into each other in 6 billion years. Let's take a look at that. So here you've got the Milky Way galaxy. That's awesome. That's taken from Earth. There's the Andromeda looking all awesome out there. That's in 3.75 billion years. That's what it'll look like. It's coming right at us. You start seeing the Milky Way bending. That's because the gravitational forces are torquing and ripping us apart. That's in 4 billion years, and you really see the Milky Ways getting a beating, and you've got the Andromeda galaxy starting to flare out. It's starting to have these tidal torques. Oh, sorry, guys. Tidal torques, which actually start ripping it apart. And in 6 billion years, we end up as an elliptical galaxy. Bye-bye disk galaxies. Bye-bye Milky Way. So that's our story. Sorry, I know that's not very cheerful. I know we want to say hopeful things and beautiful things for astronomy. But yeah, that's the truth, guys. I'm sorry. So we end up as an elliptical galaxy. But this is cool. So check this out. So remember that whole pattern thing? I found sheets in the universe and all. Right. So I did the same thing, but I replaced us, the Milky Way and the Andromeda galaxy, with an elliptical galaxy. I just figured it might be out there, right? It would be pretty cool. Well, it turns out I found 394 sheets like ours with an elliptical where we expect the local group, the Milky Way Andromeda. This is pretty novel, right? Because I can look at these sheets and see what we'll be like in 6 billion years. So I can use something now to look into the future. This is very rare. Normally you can do astroarchaeology, you can look into the past, but looking into the future is extremely odd. So speaking of looking into the past, this isn't a very exciting plot, but what it is, it's some of the best candidates of our neighborhoods that I found in our universe, real thing, and it's a distribution that basically shows you the time you're looking back at them. So remember, in astronomy, when you collect light, from any objects. What you're actually doing is you're looking back in time. Because it takes time for light to come to you. Light travels at a finite speed, it's not infinite, so it takes time. So every object, every copy of myself, of the local neighborhood, that we find that's at a good distance away from us, we're actually probing our history. And so we can actually see the evolution of our neighborhood in the cosmos. And so you can see we can peer back pretty much to 2 billion years. I have confidence in these sheets, and that's about as far back as we can go. That's still pretty cool. So we got 6 billion years in the future, 2 billion years, we got 8 billion years. That's more than half the age of the universe that we can sort of start playing with and start figuring out how our neighborhood actually evolves. Additionally, what we can also do is run simulations yet again. We have to trust them, we have to make sure they work well, so we need to compare our results. But if they do, if they work, we can use simulations to then do all the other work and go all the way back, take our little neighborhood and run it back in time and see the very beginning, what exactly happened at the beginning of time. So in summary, what I've been able to show you is our neighborhood is a pretty cool sheet with a circular arrangement of galaxies called the Council of Giants. And I've been able to show you that since the theme of the festival is evolution, I tried to focus a little bit on that, we can actually peer into the past. The present situation that we've been able to solve is we found the local group, Milky Way, the Andromeda Galaxy, has flipped their neighbors, which is pretty neat. And we can look into the future and understand the elliptical galaxy situation that will become. And that's everything, guys. Thank you very much.
Thank you very much, George.